Hi everyone, and welcome to this new video about AC steady-state power analysis. This is our example number 5. In this example we will consider a RLC circuit. It's a little bit complicated. We have two resistors, R1 and R2, one inductor and one capacitor, and there is a voltage source Vs. The values of these elements are shown here, and the questions are the following. Calculate the apparent power. S, calculate real power, true power. P, calculate the reactive power, and calculate the power factor of the complete system. Okay. Now, since we have an RLC circuit, I don't know yet, with given information, if it is an inductive or a capacitive load for this capacitive system. I don't know if it is a capacitive or inductive system. So I might sketch the power diagram, but I don't know if it's a positive phase or negative phase for the current. So it is at the moment very difficult to determine that. Instead of doing that, I will determine the total impedance, which is seen between the terminals of the voltage source Vs. So that's what I want to do first. So let me make this clear. So what is the impedance seen by the voltage source Vs? Now, the impedance S is actually a series combination of the R1 and the impedance, what you see here, the combination of these three components. So if I denote this node as A, and then we can say that actually the ZA, the impedance actually at of these two branches, is the parallel combination of this impedance, which can be given a name, and parallel combination of this impedance and the reactance of the capacitor C. Okay, if I now denote this impedance, which is the series combination of the inductor L and the resistor R2, and I will denote this as ZP, I can now write down the following: R1 plus ZA, which is the total impedance seen at point A towards ground, is the series combination. But I know I need also the value of ZA. So what is ZA? ZA is equal to ZP parallel with the capacitor reactance, so XC. Okay, and ZP is also equal to R2 plus the reactance of the inductor, so this is JXL. So I have actually two unknowns, XC and XL. So let's calculate both of them using the given information here. So XL is equal to omega times L, and omega is shown here, which is 1000, so which is 10 to the power 3 times 0.005 for 5 millihenries will result in 5 ohms. If I now do that for the capacitor reactance, so 1 over omega times C, again the same procedure, 10 to the power 3 for the omega, and we have 40 micros, so 40 times 10 to the power minus 6 will result in 25 ohms. So I have now both of the unknowns here, so I can continue with the calculation of ZP, and after that I will continue with the calculation of ZA, and then I have the total impedance. So let's move on to ZP, which is 8 plus R1, R2 times J5 ohms. Okay, that's actually for this situation. I can of course convert this to the rectangular of the polar notation. Let's do that for this case also. So it's 9.4 phase 32 degrees, and it's in ohms. What is the value of ZA? ZA is the parallel combination shown there. So it is actually ZP times minus JXC divided by ZP minus JXC. Okay, now if I now substitute the values, I have now calculated the ZP in rectangular form. I will substitute this here. I will substitute the 25 times minus J. So I have the following: 8 plus J5 times minus J25 divided by 8 plus J5 minus J25. Now if you arrange this and simplify the expression, you will get 8 minus j20, and on top of the expression you will get 125 minus j200. Again, simplifying this will result in 1 of 10.8 plus j 1.94, of course, in ohms. Okay, now we know the ZA, and we are almost done with our total impedance. So then, what will we have? And I will continue with the blue. The Z is equal to 3, because that's R1, and then 10.8 plus J 1.84, which will result in 13.8 plus J 1.49 ohms. Now, I can convert this to the polar notation, so that is 13.9 phase 8 degrees. Now, if I now write down or sketch the diagram, impedance diagram for this, what do I have? Let's do that. Because the positive phase, so we will use the positive of this diagram. So we will have the imaginary and the real axis. I have a vector length at the real part of 30.8, and for the imaginary I will have 1 point. That's of course not to scale, just give you an impression, 1.94, and for the total impedance I will make it in blue, which is the vectorial sum of the both of them, so it will result in this arrow, which is Z, and the phase here I will denote it as theta. Theta is here 8 degrees, and the absolute value, the magnitude of Z, is equal to 30.9 ohms. Okay, that's actually the situation here. Now I can move on to calculation of the total supply current, so that's actually also important. So let's move on with the calculation of IS RMS is equal to VS RMS divided by the Z, which is the total impedance. But to calculate this current in RMS, I need also the VS RMS, which is equal to Vs, the amplitude of that, divided by the square root of 2. Why? Because this is a pure sine expression, sinusoidal expression, sinusoidal signal, so I can go through the official formula for calculating RMS value, but you will get the amplitude divided by square root of 2 as a formula. So we'll have 6 divided by square root of 2, which will result in 4.24 volts. Of course, I would like to continue with the phasor notation, so I will look at the expression for the voltage source Vs, which has a phase orientation of 0 degrees, so I can also substitute that in the expression. So what do we have? We have the following: I S RMS will be 4.24 phase 0 degrees divided by 13.9 phase 8 degrees, and this will result in the source current RMS value of 0.305 minus 8 degrees amperes. So that's actually the situation, and you already know, because it is the minus sign for the phase, for the source, and you know it is a lagging. So this circuit is in effect an inductive circuit, so it is a lagging power factor. We already know that. Okay, now I can continue with the calculation of the powers. So that's actually the next step. So I will use this value and the expression for the impedance, total impedance. Then I will continue with the calculation. I will a little bit zoom it out so we can see the complete picture. So I will now continue with the powers. So for P, the real power or the true power, we know it is IS RMS squared times the real value or real part of the impedance, total impedance, which is, and I will ignore the phases, which is not interesting at the moment, only for the power factor. So 0.305 quantity squared times the real part, which is this. Actually, this is the real part. This is the real, and this is the imaginary part. So I will use those values for the P and the Q. So I will have 13.8 times the 0.305 quantity squared, which will result in 1.28 watts. Now Q in a similar form, Q is IS RMS quantity squared times the imaginary part of the total impedance, which is again looking only at the amplitude of the current, 0.305 quantity squared times 1.94, which is 0.18 volt amperes reactive. So okay, I have now both of them. Using these two, I can express the apparent power, and I know it is a lagging and it is a phase is positive. I can express this as follows, as plus, because it is inductive load, as plus JQ. Now, if I now write down what I have for P and the Q, which will be 1.28 plus J 0.18 VA. And if I now convert this to the polar notation, which will be equal to 1.29 phase, again 8 degrees, which is of course not surprising because we already had the 8 degrees from the impedance diagram. So the power diagram, if I now draw the power diagram, which we haven't done at the beginning, since we didn't know if it is inductive or a capacitive load, but we know that at the moment. So I have now a real part which has a length of 1.28. There is an imaginary, or there is a reactive part which is J 0.18, and there is the total of that, the vectorial sum, which is the S here, and which has also the same phase theta. So theta here again 8 degrees, and S actually in amplitude will be 1.29 volt amperes. Alright, that's actually the situation here. Now let's move on to the last part, which is actually the power factor, which is not really difficult anymore. So power factor, which is lagging, we already know. So PF is equal to cosine of theta, and we already know it is lagging. So let's write it down. Cosine of 8 degrees lagging, which will result in PF 0.99, almost 1, and still lagging. So it's actually almost unity. So this circuit almost has a complete power delivered to the real components, or the ohmic parts of the system. So that's actually the whole procedure for this example number 5. We have dealt with the RLC circuit, a little bit complicated than the other 4 examples, but this procedure is again exactly the same. You start from the total impedance, then go to the total supply voltage, and using the imaginary and the real parts of the total impedance and also the current, you can calculate the real and the reactive powers, and of course go from there to the apparent power and the power factor. I hope this will illustrate the concept again in more detail with a little bit challenging example. And don't forget to share this video and to like, and I see you next time, and have a nice day.